Good afternoon. My name is Jean-Louis Briot. I'm a professor and the holder of the Spencer J. Buchanan Chair in the Department of Civil Engineering at Texas A&M University. Here's the program for this afternoon. First, I will introduce Professor Rosowsky and ask him to make some introductory remarks. Then Professor Albany will introduce Professor Reese, who will deliver his special lecture on the topic of unique applications for the design of piles under lateral loading. Then I will have the pleasure of introducing Professor Alonso, who will follow with his 2003 Buchanan lecture on the topic of exploring the limits of unsaturated soil mechanics, the behavior of coarse granular soil, and rockfill. A bit of administration details. We no longer advertise the Buchanan lecture by a brochure in the mail. We send emails to a list of addresses established over the years, primarily from those who give us their email address in the guest book. We're going to circulate the guest book. If you want to know about next year's lecture, put your name and your email address. We don't need anything else. The first thing we do next year is to check the guest book and send emails to those who put their email address. You may also check the website. You've received the booklet of the Buchanan lecture. On the cover is the website, and you can check that website around July of 2004 to find out who the 2004 Buchanan lecturer is and when the lecture is going to take place. Now let me call on Professor Paul Rosowsky to give a few words of introduction. I've known Paul for a good number of years. It has truly been a great pleasure to work with him and under his leadership. If I had to pick two words to characterize Professor Rosowsky, I would use enthusiasm and energy. He works fast, he works very long hours, and he pays great attention to details. He truly leads by example. Professor Rosowsky is interim department head in the Department of Civil Engineering, and I have asked him to say a few words of introduction. Paul?
Chris, I'm going to pick on you. He's from University of Texas at Austin. He's not from A&M, so I have to teach you a little manners. It's not your tie. It's what we say around here. So when we say, we don't just say hello and good morning and stuff like that. We always say, y'all know, everybody respond when I say, howdy. Howdy. Good. Chris, every time, that's the way we go through it. Dr. Briot gave me about 1 minute, so I'm going to steal about 2.5 or maybe 3. He said a little mini intro on the Department of Civil Engineering. I never stick to what he told me, so don't be mad at me too much. Everything is new at Texas A&M. We have, for example, a new president, a new dean, Bennett, and most of all, we don't care very much about the other two, but it's the football coach, and we're having some problems with that. Everything is new, including the department head. We got 4 candidates maybe. David Rosowsky, Oregon State, wood person. I'm characterizing these people a little bit. Another candidate is coming, Jeff Russell from construction engineering. Another one, Deborah Thurston, general engineering is her specialty. And Juan Valdez, water resources. He was a former professor here. They're coming in December. We'll have a replacement for me. Boom, I'm out of here, which is great. So we'll be doing some new things here. Making the grade, we only got a 10 last year in U.S. News and World Report, but lucky for us this year, boom, hopped down 1 to number 9 in the undergrad program, and luckily, again, number 9 in the graduate program. Not good enough, Chris. We need number 1, but we'll get there with your help when you come here for graduate school. Distribution of undergraduates, just briefly, freshmen, 201, 19, and so on. We're about 881, by far the biggest civil engineering school in the United States here. Showing graduates, here's all the little schools. Chris and Professor Reese is here too. Where's UT Austin Blue? It's a good one. Here's the other one, Texas Tech, and all these other good schools. We're equal, Texas A&M's equal to the summation of all those other guys put together in terms of graduates, civil engineering graduates. It's good. It's good. We're happy for that. It's a little heavy for us. Here's the graduate enrollment. In the olden days, 94, lots of students, down, slowly, and boom, this year could jump, and it's mostly because of the students in here. The geotech students, I'll show you in a minute, boom, they shot us up to the moon. U.S. students also increased, as well as international students. We're really happy for that thing. Another one, graduate enrollment, is also up here. You can see where that's now at close to the male-female relationship. More females and also more students in general. We're trying to work on all of those numbers. Civil engineering graduate degrees, for example, here's Master of Engineering, no thesis, Master of Science with thesis, PhD at the top here. We like it that we're giving more Master of Engineering, but the problem is we need more Master of Science students. We're going hungry for those people who will do thesis research, for example. So Chris, we need you, really. We'd be glad for you to come. Here's a distribution. We like it because it's pretty uniform. Structures about 60, ocean 47, transpo all the way around. Geotech 40, most we've ever had in the whole history of the school as far as we know. It's a great testament. Dr. Brio stole my slide, but it's okay because what I'm pointing out here is our smartest student is one of the youngest ones. The other thing, he and I are interested more in the surface here, tennis. We play every day. Dr. Alonso, we talked about tennis here. We play every day. Y'all come join him. I heard rumor you beat him in tennis tonight at the reception. Chance for an extra early graduation or A+ in the class, whichever one you want. Here's a new building we're working on, at least trying to. Some of you from A&M recognize the balcony here. This is the Civil Lab building. We're working with some donors to try to work on this kind of building, plus another extension for student services and so on. We hope to do that. We're dreaming all the time here, Chris. But not only about that, this is pretty amazing news. This advertisement was on the back of the Chronicle for Higher Education, a magazine you all don't care about, but administrators wake up in the morning, they go out to the ditch in front where they throw the papers, and we read this thing. It says we're hiring more than 100 new faculty over the next 4 or 5. Actually, that's low. The lady today said, oh, we just rounded down. This is Texas A&M. It's really about 115 or more here to hire in the next May 4 years. Well, that's no fun. This is civil engineering. That was all of engineering. Civil engineering, we hope to hire in the neighborhood of 12 to 15 plus, more than that, in other words, only in civil engineering in the next 4 years, where you're going to see a lot of new faces, we hope, next year. We're starting on this already. We're looking for about 4 or 5 professors already. And this one, the plus, the dean said, if you find a hot candidate, boom, we'll give you more. So we're looking for you, Chris, to graduate from the program and move right in to help us here teach. A little bit about our vision. Global education. We love it that Professor Alonso came from Spain, for example. Another foreign country, Dr. Reese came from Austin. We have globalization here. Globalization is a key part in our thing, but I wanted to share a little bit with you our thing. Advanced computational technology, Chris, instead of hiring geotech, structures, construction, that kind of stuff, we put a big X on that and we said, no, let's have some vision areas, and if we find geotech people, great. 3D computer graphics, simulation, and what we want is inter stuff. We want to work, for example, with computer science, architecture, and civil engineering across the way. So we're looking for faculty members in these kinds of areas. Sensors and monitoring. My microphone doesn't work too well. We need a better one. Lots of them. We want, for example, Dr. Biscontin. She said, give me about 100 MEMS, little bitty thing. Throw them in the ground, mix it up, put that in the foundation of the building, and then we want to read those frequencies back and parallel process them through some heavy computers. Got to get with computer science people to do that, electrical engineering. Another field, sustainability. The transportation people love that one, but we also do that in geotech and other areas. Work, for example, with architecture, preserve old buildings, old foundations, work on preservation. Another area, homeland security or vulnerability, risk analysis, reliability. Turkey yesterday, we were talking at lunch, blast loading. Bush School would work with us on public policy. Lots of things to dream about here, visions. So we thought about this. We said, wow, let's go out and find some people. So we sent Dr. Biscontin out. She went to Barcelona just per chance, and we told her, see if you can find Dr. Alonso, talk to him a little bit about geotech. She took these nice pictures. Thank you, Giovanna. We appreciate that. It was nice, Barcelona, the sea is out there, and we asked her to find him. She went all around taking more pictures there in Barcelona, some nice stuff, but she couldn't seem to find her. So I told her, go look in building C1, is that right? I think it's building C1, and see if you can spot him in there. And she looked, this is the lab there in Barcelona, kind of boring a little bit, and she said, well, the student said he's out doing some other stuff. And she said, where? And I said, oh, wow, this looks like a good thing. He's a sailboat enthusiast. Sure enough, he wasn't there, but we finally found him. It's a little hard to spot. He's a little bit hard to spot here. It was fun. Oh, well, less fun, though. Thank you for coming. We surely welcome you. Then we sent her on another trip, University of Texas. Go see if you can find Professor Reese. We looked all over the place. We found some fun places, though. We didn't really find him, but we found some things to look at. So I think we're ready. Dr. Reese, you're going to be the first up after we finish here.
Okay, our first speaker is Professor Lymon Reese. He's an emeritus professor from University of Texas at Austin. A little bit on his background. He was chairman of the Department of Civil Engineering there from 1967 to 1972. He was associate dean of the college from 1972 to 1979. And presently, he's a principal of Ensoft. It's a distributor of engineering software, and he pursues consulting through Lymon Reese and Associates. He's got his bachelor's and his master's degree from University of Texas at Austin, and he got his PhD from University of California at Berkeley. He has done extensive research and he has published widely. He has published over 400 technical publications, and in particular, he's most particularly well known for his work on laterally loaded piles. And anybody that's done any work with laterally loaded piles is familiar with his field studies on instrumented piles. Briefly, some of his awards. He was a Terzaghi lecturer in 1976, and he received the Terzaghi Award in 1983. And some other awards, he's was awarded the Joe J. King Award by his peers at UT Austin in 1977. He received the Offshore Technology Distinguished Achievement Award in 1985, and the Distinguished Graduate Award from UT Austin in 1985. And he's been a keynote lecturer at a large number of conferences, just itemizing some of them. International Conference on Calcareous Sediments in 1978, International Geotechnical Seminar on Deep Foundations on Bored and Auger Piles, and the Second Symposium on Geotechnical Problems in Saudi Arabia in 1989. And last but not least, he was elected to membership of the National Academy of Engineering in 1975. So without any further ado, we're now honored to hear Dr. Reese speak.
I'm going to talk this morning about a topic which I think will be of interest to you. And at the outset, I'd say I want to recognize my two co-authors, Jose Arreaga and Bill Eisenhower, neither of whom could be here today. I'm going to talk about technology. That technology, one of the things involved in it is being able to predict the response of the soil to the lateral motion of a pile. We call those PY curves. Those are nonlinear curves. And I'll give you some idea about how we obtain those kinds of curves. Then we have to implement that technology, and that implementation involves the solution of a fourth order nonlinear differential equation. When I heard that term as a graduate student, it scared me to death. How do you solve a nonlinear fourth order differential equation? But with our modern computers, it's duck soup. So We don't worry about that much. We worry about how to do the coding, but the solution is readily available. Talk about some field tests, because we cannot, in regard to piles under lateral loading, predict the results based purely on analysis, on small-scale tests, but we have to get in the field, and I'll show you some of those. I want to talk about some current applications, because this technology is being applied in many ways by many industries, many countries in the United States and abroad, and those applications are very interesting. We talk about some of the frontiers of knowledge, where we need to go. We're not through yet. We need to move forward in several areas, and I'll have some concluding comments. The technology means that the analysis of a pile under lateral load depends on two features, as I mentioned earlier. We have to predict the nonlinear relationship of the soil to lateral deflection of the pile. The valid solution of the nonlinear equation, it's a beam column equation, because we need to consider not only the lateral load and moment at the top of the pile, but also an axial load. So we're solving a beam column equation. With regard to PY curves, the concept was presented first by McClellan and Fote in a paper in 1958, and the results of a study reported by Texas A&M University was available to McClellan and Fote. That report came out in 1952. It had to do with the results of the load, lateral load put on a pile next to an existing drilling platform. Those two authors looked at that result and said, well, we think we can model the soil in a nonlinear way. We're going to call the deflection Y of the soil and the soil resistance P, and we're going to say that that formulation, that way of thinking of the soil, is going to vary with depth and with soil conditions, with pile size, and with nature of loading. So those concepts came out very early and have been built on over the years. The first major developments came when Shell had an offshore platform to put in 82 feet of water in 1952 in Block 42 off the coast of Louisiana. That was a great step forward. Before that, we had what was called Texas towers in some places. Those towers were put in for radar installations off the east coast of the United States as a way to protect the country, and in more shallow water along the Texas coast. And they got the name of Texas Tower. The concept was that you built a template or a platform that could be set on the ocean floor. It had open tubes that could be used for guiding the piles that were driven. The piles were welded off at the top of the platform. A deck was set on. This could all be done very rapidly, and that rapid construction was needed in order to avoid severe weather that comes frequently at some places offshore. Shell began discussions in 1955, a half century ago, for field tests that could lead to a better understanding of this problem. Prior to those discussions, Shell held a meeting and asked two consultants to come forward and present a solution to the problem of Block 42, 24-inch diameter piles. they got widely divergent results from the two groups of consultants that sat in a room and talked to each other. From that point forward, they said, we'll need some research, and wisely they selected to do the research not in the laboratory, not by pencil and paper, but with regard to full-scale field test, and that concept is still valid today. They made a contract with Hudson Matlock and a group of his associates who began these early works. The first comprehensive report on results of the field test presented sometime later on to the Offshore Technology Conference in Houston, and Matlock presented a paper in 1970 based on the PY curves for soft to medium clay. PY curves predicted both for static loading and for lateral loading. And it's of interest to note that the results presented by Matlock are still being used by the offshore industry and others, and are reported in publications of the American Petroleum Institute, the Federal Highway Administration, and others. The technique that was employed was to instrument a full-size piles at close spacings along its length, and to make a measurement of bending moment during the application of increasing loads in increments. So the load started at a very light level, increased, and with the close spacing of the instruments, a bending moment curve could be developed all along the length of the pile. With those bending moment curves, deflections came from double integration of the bending moment curves. And the difficulty arose by getting soil resistance, because that required double differentiation. If you've tried to differentiate an experimental curve, you know that the errors just multiply as you move forward with the differentiation. What Matlock did is of interest. Electrical resistance strain gauges were used. He had a 6-inch drum of plastic with a spiral groove cut in the edge of the drum, and about an 1/8 of an inch copper wire placed in that groove. In order to balance the Wheatstone bridge, the drum was rotated until you got a null balance, and the drum was calibrated, and he was able to read lower than 1/1,000,000th of an inch per inch in terms of the strain, which then could be translated into bending moment. I don't think anybody else has used that technique since, but it worked fairly well for Matlock and his group. The problem occurred because with the large loads, as you moved up on the loading curve, you would have creep of the soil under that lateral load. You were holding the lateral load constant, but there was creep. So the instruments were read down the pile and back up, and an average made to get the reading at a particular moment, introducing some error. But on the whole, his research was very successful. I want to point out that research technique remains valid today, and we still have the opportunity to make use of it. The problem is that it costs quite a bit of money. You have to assemble a rig to do the construction. You have to do the instrumentation, which is expensive. Weeks are spent in preparation and doing the testing, and very few agencies are interested in spending the money for that type of research, even though we still need research of the same sort. We'll show an example of the testing technique. This was not done by Matlock, but done at some time later on. And this has to do with the test of sand, a site where there was sand, and we want to be below the water surface. As I mentioned, these early research studies were funded by the oil industry. So they wanted results where the water table was above the ground surface. And there was a very good reason for that. What we had to do then is to extend the results into applications for all kinds of designs, but the data from the test below the water surface were valid for other applications. Shell had a site on Mustang Island where they had a tank farm, and some information was available on the soil conditions at the site. I'd say that in many instances, trying to do research of this sort, one of the most difficult things is to find an acceptable site. We needed a site where sand existed for quite a depth, and we had, in this case, a sand about 40 feet below the ground surface. Also, you needed some kind of uniformity in terms of soil characteristics. I'll not show all very much detail, but just show the grain size distribution curves. These curves are for fine sand, as you can see, and pretty uniform grain size in the fine sand range. We're going to do tests now in fine sand, and we know that the grain size distribution will vary. We'll have coarse sand, we may even have gravel. So what do we do in order to extrapolate the results from testing in fine sand so that it's more widely available? We take the results, and I'll show how we got those a little bit later, from these tests. Then we search the literature to try and find as many lateral load tests, perhaps uninstrumented, where maybe the only measurement was the load at the ground surface, soil properties, no instrumentation up and down the length. So we have the ground size, ground surface response. We can take our results from these tests and make a comparison for the ground line response in other types of granular soil. And that way we are able to gain some confidence that the results of these tests can be used elsewhere. Just to show the extent of the research, here's a plan view of the excavation that was made. You see it was about 50 feet by 30 feet in dimensions. The reason we made an excavation was to get below the water surface and to take away from the ground surface some soil that was not uniform. Here were the piles that were used at this site. These were 24-inch diameter pipe piles. The reason we have two piles is that one of them will be tested under static load, and with that type of loading we get a background curve that we can compare, a backbone curve I should say, that we can compare with the results from the soil properties. Then the other test, one static loading, the other lateral loading. And in regard to the lateral loading, there's a lot of phenomena involved. It's very difficult to predict analytically how a pile is going to behave under lateral loading. Therefore, we're dependent on the result of a number of full-scale field tests for that information. So we have one set of results for static loading, and then we can see what happens to those PY curves if instead of static loading we have repeated loading. Here's an indication of the strain gauges that are put inside the pile. And what we had was the fortunate circumstance that we had a fellow of small size, small stature, working with us. And you get on a scooter like you get under an automobile and go down on the inside of the pile. Oh, it's necessary at each location to grind away the surface, clean the scale off the steel, very carefully affix the strain gauges, and then what we see here is waterproofing. So that was accomplished by a worker moving down on the inside of the pile. Here shows the cabling from a whole series of strain gauges up and down the length of the pile. Here's a very important consideration. It's not especially a good slide, but what we have is a calibration test in progress. Right here we see a hydraulic ram and a load cell, and we're putting applied loads through a particular point through this plate right here, which gives us an exact position. Then we measure the results in terms of the strain gauge reading up and down the length of the pile. Knowing the bending moment, then we have a calibration curve for strain gauge reading as a function of bending moment for every position along the length of both piles. Those calibration curves could be developed analytically, but we get a more precise result using the calibration shown here. This shows the installation of the reaction frame using H piles, and you can see the fabrication of the reaction frame right here. All of this, of course, is carefully designed and carefully installed. This shows an elevation view of the reaction system. One pile under static loading, a second pile under lateral loading. And what we show here is we have 2 points on an unstrained section of the pile, an unloaded section. And those 2 points will give us the deflection and rotation of the top of the pile at the point of loading. Then with the load cell right here, we will know the lateral load, and you notice there's some distance between the load cell and the ground surface, which gives us the applied moment at the top of the pile. So we know 4 boundary conditions: rotation, deflection, shear, and moment for each of the increments of load that we apply to the pile. This shows the pile driving operations. Assemble a pretty good size construction rig at the site. Driving with a Del Mag hammer, and we'll see somebody here with a transit looking at the pile that was being driven. Some of the things that we didn't take into account, and there were a number of them that we had to take into account and adjust to, was the fact that as this pile was driven, it rotated. So the workman down here put a clamp on the pile, got a long moment arm, and twisted the pile so that instead of the strain gauges being right on an axis of the loading, the strain gauges would be off to one side. So we pulled the strain gauges back so they were precisely in the direction of the applied load, something we didn't anticipate that we'd have to do. This shows some of the field operations, and they were time-consuming and sometimes difficult. We had a cover over the piles to keep the rain out, but still we're pretty much in the weather. As you see now, we have protection for the ram and the load cell. The load cell was calibrated in the laboratory so that whatever reading we got, we could convert right into lateral load. This shows the unloaded section above the ground line and 2 points where we're measuring deflection. We took a look at the ground surface, and one of the things we did was observe the movement of the soil some distance away from the pile. And under cyclic loading, there was some densification of the soil because of the cyclic loading and also due to pile driving. But the main thing of interest was that we could see movement of the soil as much as 4 diameters away from the pile, which meant that if you had piles in the vicinity, we would have to count on what we call a pile-soil-pile interaction. So we have to make adjustments if we have a pile group to design to take into account the influence of one pile on an adjacent one. Now, I'll not show the PY curves that were developed here at this site, but just move ahead to where we make a comparison between the use of the PY curves to compute bending moment and the bending moment that was measured for a load of almost 60 kips. And you can see that we're able to compute fairly accurately. So the integration and differentiation and the cross-plotting we did appeared to be working fairly well and gave us a pretty good agreement between calculated values using the PY curves we developed, the criteria, and the applied load. Notice that we put on this 24-inch pile, this is static loading, a fairly significant load. When I was in graduate school, I was told that the New York Building Code would allow one to put on 1 kip lateral load on a pile unless a load test was run in the field. Here we're putting 60 kips on a 24-inch pile, which is a fairly significant load. Now here's the result for cyclic loading, again up near the maximum bending moment, somewhat less load and about 55 kips now instead of 60. And again, with the PY curves for cyclic loading, we're getting a reasonable agreement or good agreement between the computed values and the ones that were measured by the strain gauges. So we have a set of PY curves that work very well, and as I mentioned before, we'll use those PY curves and glean all the data we can from the literature on uninstrumented tests. Very few instrumented tests have run to give us some confidence that the PY curves are giving us reasonable values. Now we turn our attention to the 4th order nonlinear differential equation, and we'll see the terms of that equation. The EI value is the stiffness of the pile, and that's going to vary with with length, and with our computer program, we can also take into account the change in stiffness with bending moment. So we can use the same equation to analyze a reinforced concrete pile where this EI curve is going to vary with bending moment throughout a wide range. Y is the deflection, X is the distance along the pile. Here's the axial load, and that axial load times the second derivative of Y with respect to X gives us an idea of the influence of axial load on bending moment. Here's the secant to a PY curve, and note that the PY curves are going to vary with depth, and also with every deflection we get a different value of this E P sub S, which is a secant to the PY curve. Here's the deflection. W is a distributed load. This same equation could be used for analyzing a pile supporting a retaining wall, for example. And in that case, we'd want to use distributed load. So we have a very versatile equation. Can be used for steel piles or reinforced concrete. What we like to do is to solve this equation for our particular case using a set of PY curves for the soil in question. The soil may vary with depth. It may be layered. The loading may be static or cyclic. So we have those PY curves that predict the behavior of the soil as well as possible. What we'd like to do then is load the pile as much as we can and solve this equation for the bending moment along the length of the pile. We get out of this equation deflection. The second derivative of the deflection gives us a moment, the third derivative shear, and so forth. So the solution to that equation then reveals the entire behavior under that particular load. What the computer program does is automatically, internally, vary the EPY values so that we agree with the secant on every PY curve along the length of the pile and do repeated results. This is nonlinear, and then we'll reach convergence. That convergence would be achieved with a light load. We put on a somewhat heavier load, go through the solution again, and stack up on the computer a whole series of loads, which means a very simple entry on the computer. We simply modify the loads. And we're looking for the load where the bending moment determined from the second derivative is going to give us a plastic hinge. That's where the pile is going to fail. The second derivative is this deflection Y. Second point, I should say, is that the deflection Y may be excessive. In some instances, the design may require a limited deflection. So in that case, we're looking for the load that will give us a limited value of Y. In most instances, deflection is less important than the load that would cause a plastic hinge to develop. So we're looking in that instance for the maximum bending moment. Now, in order to solve that differential equation, we do it with difference equation technique. The pile is divided into a number of increments. We can see the increments right here. This is y point m, ym minus 1, ym minus 2, ym plus 1, ym plus 2. So with the 5 points of deflection along the length, we can write the solution to the differential equation in difference form, and here's what it looks like. You see this px here, which is the axial loading, so that term gets in there. H is the distance between increments. So the way we solve this differential equation is to select a number of increments into which the pile is divided. We go through and make a solution and look at the results. Then we change the number of increments to see if we have divided the pile finely enough and look for the result again for the same particular loading. If we get the same result, we have assumed that we've divided the pile into a proper number of increments. The other technique we use to check to see whether or not we're getting a useful solution to the differential equation is to make a solution using the difference equation for a closed form solution. And if this EPY is, which we see here, is constant with depth, then we have a closed form solution to the differential equation, and we can compare the results using the difference equation to that closed form solution as another way to check our result. Now, with regard to the application, current applications of this method, we see fixed offshore platforms, bridges, high-rise buildings, wind farms, a lot of those are being built, overhead signs, waterfront structures, locks and dams, earth pressures, I mentioned that, transmission lines, towers, and other applications. This shows the offshore platforms, and this is still an important consideration. Many of these are in deep water, but even in deep water, frequently there's some kind of anchorage that's necessary. This is a jacket structure, and you'll see here's the bottom of the structure, and it's set down on the ocean floor, and piles are driven through these jacket legs. Here's another view of an offshore platform. These photos came from ConocoPhillips. One of the things you can see just in passing is that as much as is possible, the structure is as sparse as possible above the water surface that is going to occur during the storm. This would be the height of a wave that is predicted to occur at that particular site, so that the wave crest does not impact the platform itself, but merely passes through where the legs are. Sometimes the operating people put all kinds of things down here to the dismay of the designer. This shows a bridge in Austin, and the foundation of this bridge is on drill shafts, and as you can see, they'll be subjected to lateral load and axial load. This is a high-rise tower. Here's where a load test was being run in Los Angeles, and this tower is the Dreamworks in Universal City. But a tower like that will sustain substantial lateral loads under wind conditions. Here's a offshore tower to generate electricity, and these things are being built around the world, both onshore and offshore. This shows a dock and a large ship next to the dock, and as that ship moves against the dock, energy has to be taken out by a system shown here, and we'll talk more about that later. This shows a lock and dam. This happens to be a recent picture on the Monongahela River near Pittsburgh. And this thing was constructed by putting drill shafts in first and then floating in the structure and setting it down on the drill shaft. And as you can see, that structure will be subjected to a considerable amount of water when the water level is raised behind it. This shows another type of application where we use the PY curves. This is a retaining wall supported by drill shafts in Houston. And as you can see, earth pressure will apply against these piles, and there will be a bending moment and shear right here, and there's got to be enough pile below the ground surface to sustain that lateral load. This shows transmission towers, and this particular one, as you can see, this tower sustains an angle in the transmission line. So there's a lateral force which has to be transmitted to the piles down below, in addition to forces due to the wind. Now we're going to talk about two what we call unique applications of this technology. One of them is an anchor pile for a floating structure, and the other one is a berthing system for a large ship. These are not the normal applications of this technology. But this shows some floating structures. This is perhaps a drill ship, another offshore floating structure that has to be anchored against the wind forces and perhaps wave forces offshore. This shows a structure that is just used for seismic testing. Here's a drill ship, a drilling and production platform, and here's a floating production and storage vessel. All of these systems have got to be anchored except for the seismic ship on the ocean floor. And this shows the drill ship. Here's the anchor line coming down, and this happens to be a site in Nigeria where there was soft soil. So the pile was driven to 6.3 meters below the mud line here. The pile was 30 meters in length. There was a bracket here, and the anchor cable was attached to that bracket. We need to know the position of the anchor line after the load is applied, and what kind of lateral and axial force will be applied to the pile. If the axial force is too great from the anchor line, the pile will be pulled out. If the lateral force is too great, we'll have the pile failing either by excessive deflection or by a plastic hinge. And here's the scheme we worked out for making that solution. We took a departure angle from the bracket and a short length of the cable and a very small angle alpha. We calculate the cord length. Then we can get the force against that section of the anchor line by whatever tensile force is applied, and then we can also get it by the earth pressure which is applied here. Here's the tensile from the anchor cable. Here's from the earth pressure, and that earth pressure we get some by use of a bearing capacity coefficient times the undrained shear strength for this clay times the diameter of the cable. We work out those equations, and from those equations with a given small angle of alpha, we can calculate the cord length, and also we can calculate the coordinates ahead, the x and y values at this point in the cable. Now, in order to get the K value, we need to know the undrained shear strength with depth, and we make a solution that the load is not going to be constant, so that there's no loss of tension over that region. We'll say the tension is the same at both ends of that particular cord. That may not be true, but that would be on the conservative side. So we select values of this departure angle, and we calculate the value of t using this equation until we come tangent to the ground surface. And if we don't become tangent to the ground surface, we change the t for that angle until we get convergence. For that case in Nigeria, the anchor pile was 1.5 meters in diameter, had a 25 millimeter wall thickness. Here's the bending moment allowed. The bracket at mid-height, as I said. The chain gave us about a 3-inch diameter from which we were able to compute the K value. The clay varied in shear strength according to these values. And the computational procedure that I mentioned was used until this departure angle that was selected gave us a critical value of 55 degrees. That's the critical value for the largest value of t, and that t turned out to be 3,580 kilonewtons. With that value of t and with this departure angle, we computed the component of axial load, and the pile was safe against being pulled out. And this shows the bending moment curve. Here's the deflection, 40 millimeters. Bending moment shown on this side, and somewhat factor of safety. I think we had about 10,000 allowable, and we're around 6,000. Here's the bending moment curve, and we feel like that we have a unique solution using the basic equations to a fairly complicated problem. Now we're talking about berthing large ships. And very large ships now exist, and I guess you may have read about many of them that are being used. One of them, I think, carries enough oil to last the whole United States for some period of time. The docking energy can be large. The docking energy must be managed, and most harbors have rules by which these ships can be docked. This shows some examples at harbors around the world. These values of displacement are fairly moderate compared to some of the ships now available, but this gives you the berthing velocity that was allowed in those particular harbors. If you come up with a berthing velocity larger than these, then either the ship can't dock, or tugs will have to be used, or some other technique used to keep these velocities below these values. Now we take that energy out in three ways, I should say. One of them is what we call fenders, and here show 3 different types of fenders. What we get from this fender is a force deflection curve. So as the ship comes against a fender, it has a curve put out by the manufacturer that gives us the force and deflection, and it may be a nonlinear value, but we have that data from the manufacturer for the various types of fenders that are built. That's one of the techniques. The second one is that We can calculate the deflection of the dock itself. It may be supported by multiple piles. And the third one is we put up a breasting dolphin, a single large diameter pile. And we're going to show the use of a breasting dolphin here. What we figure out that we had a 40,000 ton vessel. The impact velocity is 1.52 meters per second. Those data came from the harbor and from information at the site. We did a preliminary computation and said that of the multiple dolphins that we have, the ship is going to contact 2 of them at one time, but a single dolphin needs to accept 231 kilonewton meters in energy, a single dolphin. And we select a dolphin here with 1.4 meters in diameter, and they can be quite large. We worked on some on the west coast that were about 10 feet in diameter. The maximum wall thickness here was 60 millimeters, and the dolphin was tapered. By being tapered, we assume different wall thicknesses down the length. The yield strength of the steel is given. The length of the dolphin is given. Water depth here at the site was 11.3 meters, and the impact was 14.6 meters above the mudline. We did some work in the Mississippi River using one of these systems, but the problem there is that the height of the river stage would vary, and at some season the contact would be fairly short, relatively short distance above the mudline, and you may have too much horizontal force against the wall of the vessel. At another season, the water is higher in the Mississippi River, and you get more bending moment in the dolphin. So that required a whole series of computations along the river. And as far as I phoned over there some time ago to find out, and I couldn't find anybody in the whole facility that knew anything about the breasting dolphins. But as far as I know, they're still working after a number of years. At this site, we have soft clay at the mud line, and down below we have these strength values, and I'll not go into those values. But with the strength value and with the point of application, we develop a load deflection curve. Then we integrate the area under that load deflection curve, and that gives us the energy up to this point. And you see we had about 1,000 kilonewtons applied load at that point. Then we take a look and see whether or not we have a failure condition. And here's our bending moment curve for that particular docking energy. And we have some plots here we tapered. Here's the 60 millimeter steel, and that's the first yield of the steel, and this is where we develop a full plastic hinge. So we have, as you see, an appropriate factor of safety, and we can taper by reducing the wall thickness above the maximum moment and below the maximum moment to save steel. So, solution to a unique problem. Now, with regard to frontiers of knowledge, we still are in the research stage in many instances in geotechnical engineering. One of the very important considerations is liquefied soil, soil that liquefies during earthquakes. We're interested in the lateral spread. We have a number of soils that are very difficult to sample and test. I think there was a stage in geotechnical engineering where we saw a vast improvement in the methods and tools for testing of the soil. We seem to be in a kind of a lull in that regard, so there's much work to be done in regard to improving our abilities to give the properties of soil. There are a whole series of new computational techniques with the power of the computer that we have now that we can implement. Here's just a few ideas about further research that we need. Now, in conclusions, we have a powerful and versatile analytical tool in what we call soil structure interaction. I can't really show you the power of that tool very well, but if you were to sit down with a laptop computer that you took into an airport, use the codes that are available, you would find that you could investigate multiple parameters in regard to the problem in a fairly short period of time. So what we say is that here's a tool that's got to be used by a knowledgeable engineer. The students who are studying engineering here are going to be taxed to use such a tool properly. Need to know about soils, need to know about mechanics, and need to have some feeling for the problem. We had a man phone from Washington and said, we have a computer program up here and I want my secretary to be able to run this program and get a solution. Maybe so, but I say not. I say that what we need now, we need some brains to make use of these powerful analytical tools. The analysis that you can do on a particular job can indicate whether or not there's a full-scale field test may be desirable and can be funded by the difference in design making conservative assumptions and design making what might be thought of as realistic assumptions. Students who go out there and practice, use these tools, vary the parameters, and showing the difference in cost may indicate the desirability to do full-scale field experiments. Following construction, using these methods, we urge the observational method to be used. Look at the job after it's built. See as well as you can what deflections have occurred. Look at the movement of the structure to be sure that the structure is working as you proposed. And we can develop improved methods for solving this soil structure interaction problem in several areas of application. And again, the students who are here will have those kinds of opportunities. Thank you for your attention.
I was actually just curious about your strain gauge testing methods. Yes, sir. The piles, are they closed in?
Well, you have to keep the strain gauges dry. And what we wanted to do with the offshore situation is to drive the pile far enough down that we had an anchor on the bottom, but we didn't need to measure the bending moment because down there it was going to be very small. So we drove an open-ended pipe, and then we had the instrumented pipe sealed with plate at the bottom that we welded to that open-ended pipe. And that worked fairly well, but we had some experimental difficulty that I'll not tell you about, but we tried and we succeeded in keeping the strain gauges dry. You have to keep them dry.
I was mostly at the bars through the center, and the strain gauges were open on the inside. And that's what I was curious about. I figured it would be kind of difficult to maintain the strain gauges and the driving capabilities of the pile that way. But you said you took care of that. So.
We brought the cables out through the top, and we were very careful to keep the entire space where the strain gauges were as dry as possible. We used some desiccant in there, and then we had the top closed with proper exits for the cables. A very good point.
Other questions? What is the range of application of the method? You showed some 2-foot piles. These were experimental markers.
You keep asking real good questions here. What we want to say is that the piles we tested were in the range of up to 2 or 3 feet in diameter. When you come to cyclic loading for a large diameter pile, there's got to be a diameter effect, which we don't know very well. And we left a few questions for people like you. For example, what we observed with a 2-foot diameter pile, when we moved it over a foot in over-consolidated clay, a gap occurred, and that's very reasonable. That gap filled with water because we're below the water table. The next load, the water squeezed out. What happened when it squeezed out? It brought soil with it. So we had a very serious effect from cyclic loading. Now we feel like if we had a 10-foot diameter pile, that you have a 1-inch gap, that same thing is going to occur. So we don't think a 10-foot diameter pile and a 2-foot diameter pile are going to behave the same under lateral loading, under cyclic loading particularly. Under static loading, we think we're pretty confident. But when we get into cyclic, for the diameter effect, we're not confident at all. And we're still waiting for you and others in academia to give us good answers.
Don?
What would you say is the most, during your research on lateral loaded piles and trying to characterize things and so forth, what's the most difficult part of the problem? Is it the known part, analytical part, conceptually? What do you think, what was the biggest challenge for you?
With regard to the experimental work, being very careful with our instrumentation, we get a pretty good bending moment. So the difficult thing, Don, has to do with the soil. If you're, for example, we have some tests in over-consolidated clays that are vastly different under cyclic loading, where the shear strength of the soil is fairly the same. So the response of soil with regard to the particles and the makeup of the soil itself is the very difficult thing to take into account. You get PY curves, but are those PY curves representative of all the soils that are in that same category? That's our difficulty. And then that difficulty is magnified in a design problem if you have layered soils. Because a theory would show that a soft layer and a stiff layer next to each other are not going to stay exactly on that same plane under lateral loading. So we still have a lot to learn.
I wanted to thank you, Lymon, for an excellent presentation. I remember being a graduate student in the early 70s and in Canada and learning about the work of Reese and Matlock on laterally loaded piles. And I was really impressed. And to find myself standing right next to you today is really a true pleasure. And to count you among my close colleagues, it's really a great honor. Now, I have a certificate to give you, and I want you to know that in to respect your spirit of cooperation. We made the certificate maroon and white, of course. And we got a frame that is as close as burnt orange as you can find in College Station. Thank you very much. In August of this year, I lost a friend. Mike O'Neill. We prepared a CD of his Rosowsky lecture when he delivered it here in 1999. The CD is now available, and it's free of charge. If you want a copy, just let me know. At the end of Professor Alonso's lecture, I will ask Dara Hooper to come and handle the discussion period. And then after this, I will ask Philip Buchanan, the son of Spencer J. Buchanan, to come and thank our speaker. Now it is my pleasure to introduce the 2003 Buchanan lecturer, Professor Eduardo Alonso. Professor Alonso is Professor of Geotechnical Engineering at the University Politécnica de Catalunya in Barcelona, Spain. Born in 1947, he received his engineering degree from the University of Madrid in 1969 and his PhD from Northwestern University in 1973. His main topics of interest are numerous: reliability, risk, behavior of partially saturated soils, expansive soils and rocks, numerical analysis, field measurements, slope stability. He's been involved in over 90 consulting jobs in Spain and abroad, involving deep excavation, nuclear power stations, diaphragm walls, ground improvement techniques, design of shallow and deep foundations. The list goes on and on. Professor Alonso has written over 250 papers, most of them published in refereed journals. Among his most prestigious awards are the Telford Medal from the Institution of Civil Engineers in the United Kingdom, the Premio José Torán from the Comité Español de Grandes Presas in Spain, and the Conférence Coulon from the Comité Français de Mécanique des Sols in France. He is truly an internationally known engineer and chairs the ISSMGE Technical Committee TC6 on unsaturated soils. In 1995, he was elected to the Royal Academy of Engineering of Spain. I also have some first-hand information about Professor Alonso's dancing talents. Almost 2 years ago, we were at the International Conference on Unsaturated Soils in Recife, Brazil, and there was quite a bit of samba and bossa nova dancing in the streets of Recife. So in addition to all the work that Professor Alonso is doing, I can tell you that he also knows how to have fun. His talk this afternoon is entitled Exploring the Limits of Unsaturated Soil Mechanics, the Behavior of Coarse Granular Soils, and Rockfill. Professor Alonso.
Thank you very much, Jean-Louis, for your very kind introduction. It is indeed my privilege and it's a real honor to be here today to deliver the 2003 Buchanan lecture. I would like to thank the persons who selected me, and in particular to Professor Jean-Louis Briot, and I simply hope that the subject that I selected will be of some interest or value for you. Talking about Coulomb, I will start with this picture of Coulomb. Coulomb, I think in 1773, he published his well-known paper on how to calculate retaining walls. In that paper, he established also what we know as the strength law, Coulomb law. 4 years later, he published a paper on friction. And he went on enumerating the factors that control friction, the nature of the coatings and the materials in contact, the coatings and materials in contact, the size of the surfaces, the pressure, the time spent since the surface were put in contact, and finally he mentioned the humidity of the atmosphere, and this was a real insight for the time. So probably we may consider him as the grandfather of unsaturated soil mechanics. I'm sure that Jean-Louis Briot will agree with me. Let's examine briefly the soils. And we have this scale here. This scale relates, for instance, to grain size. So we have coarse soils on the left. Here in the middle we have probably, what is a silt, a fine sand. On the right, clay materials. Now it is useful to consider not only the grain size distribution, but the pore size distribution. It gives perhaps more information. For instance, for a beach sand, here you have an example of the pore size distributions and also the particle size distribution, and you see that this is a unimodal type of distribution of pores. And when you move towards the right, then you have more complicated pore size distribution. You have big pores, smaller pores, but typically you may find this type of curve relating the, this is the frequency curve. So you have small pores, you have big pores. This is a double porosity type of situation, and this applies, for instance, to many compacted soils in which you have some clay. We in general accept that the capillary concepts control the behavior of unsaturated granular materials such as silt, such as sand. We also accept that capillary concepts are useful to describe those big pores of the compacted clays, for instance, or natural clays. The situation is more difficult for those smaller pores, but I am not going to talk about the materials from this line here towards the right, but from the materials from the size typically of a fine sand or silt towards the left. What is the role of unsaturation here? Here is this beach sand. We have seen those two pictures now. And on the right here in the upper part, you have the results of some collapse test. Actually, what we did was to take an odometer, to use a very loose specimen, and then to subject it to control change in suction. So you wet it, you start at a quite dry state, and then those are the strains measured. And you see that the strains are quite small, 0.4%, 0.2%. It depends on the final suction. So when you flood the sample, you get this value here. This is for a fine sand, loose, fine sand. What can you expect if you move towards bigger sizes? Probably nothing. In fact, in order perhaps to convince you that capillarity is for relevance, this is very quickly the results of a numerical experiment. We put some effort on this. Those are spheres, and you put all of them together, and you also introduce some entities, such as the pores, and you introduce also a mechanism for water transfer, for vapor transfer, and if you are able to put all that together in a discrete way, you have a kind of a numerical laboratory to analyze granular soils. And here you have one of those numerical experiments. You load the sample at a given suction, 90 kPa, and then you wet it, and then here is the collapse. And certainly, capillary effects are of significance here, in the sense that by invoking simply capillary concepts, we are able to reproduce real tests. And, well, you may have some fun in reading this paper, which has been recently published in the International Journal of Numerical and Analytical Methods in Geomechanics. But let's abandon those theoretical ideas, and let's go to the field. And what we see is that rock fields actually deform a lot when they become wet. Here are some examples. For instance, this Martín Gonzalo Dam in Spain experienced very significant settlements, as you can see here. And it is interesting to see how different plates located at different elevations within the dam reacted, and the reaction against, in terms of strain, in a long time is indicated here. And you may see also this black curve here, which actually represents the accumulated rainfall. And you see there is a very strong correlation between rainfall and deformations up to a moment, 1,000 days, 3 years or so. And after that, you see that essentially nothing happened. The rain continued more or less the same pattern, but nothing happened. And the question is why? Those are coarse materials. Now, there have been attempts to predict the behavior of such structures, and probably we can classify the approaches in two, the ad hoc approaches, and here is a representative paper by Granular et al. In Geotechnical in 1997. What he did was to solve the dry and wet problems, apply the differences in stress, and solve a new problem, just very, very quickly. But he needs two sets of parameters. For instance, if we work with an elastoplastic model, he requires a set for the dry material, another set for the wet material, and then he's able to solve the problem without going too much into the physics of the problem. There have been approaches also based on unsaturated soil mechanics, because it had some theory, and we did some work, and more recently, Kogo in Japan has, for instance, presented some analysis of the Orobillo Dam. The point, however, is that, well, what is the meaning of unsaturation for a coarse material, for a rockfill? Let's examine if there is any hope for capillary stresses to explain what we have seen. On the left, you have an evaluation of the force of attraction between two spherical particles with a meniscus here in between as a function of this suction, and for different sizes. And this is a dimensionless quantity, so this capillary force actually is related to the weight. So this is actually a particle weight divided by the capillary attraction. And you see how, for instance, for a boulder, the size of a particle is much higher, is huge compared with the capillary force that you may have here. This is also true for the gravel. Actually, you have to go to a medium shale, to a fine sand, in order to have comparable forces. Actually, you may even compute what is the capillary stress. The only thing you have to do is to assume some arrangement for those particles, and then you may add all those forces and divide by the area, and then you have the stress. And here is the stress for different materials plotted as a function of suction. You see that in this logarithmic scale, the effect of suction is not very well marked. The reason is that there is a limit, there is an asymptotic value of the force that is developed between two particles in contact. And again, you see that those forces, those capillary forces, are very small for boulders, very small for gravel, quite small for medium sand. You have to go into shales, actually, to have a significant force. So what is then the significance of partial saturation in a rock field? Naylor, in his paper, this was the back analysis of Belice Dam, and I will talk more about this dam. He said, no attempt was made in the analysis to model the effect of partial saturation, as, for example, has been proposed by us in our model of 1990 for unsaturated soils, and because he said that this effect is thought to be small in the rock field, and I think he's totally right. Now, with this introduction, I will present here the outline of what I'm going to say. I will review a little bit more observation on the rock field, and I will present some historical review of what has been the understanding of rock field deformation and particle breakage, and I will then present the results of the first experimental investigation that we did. I will then move into a model for rock field compressibility, and here I will stop for a little bit to compare unsaturated soils, rock fields, and then I will move into triaxial states, flow and deformation, because we need flow in order to understand, for instance, the effect of rain, and then we will compare model prediction with some cases. Some observations. El Infiernillo Dam, this is a Mexican dam, quite large dam, and here you have the level of the reservoir. It was built in 1963, and then the level remained essentially constant for the next 4 or 5 years. And here you have the rain also, and here you have some data coming from some marks. For instance, this mark 23, which is located here in the downstream part of the shell. And here you have, for instance, the horizontal and the vertical and the settlement deformations. And you may notice that there is a correlation between the rain episodes and the acceleration of displacements. This is also the case for Beliche Dam. This is a dam in the south of Portugal. This is the design, central clay core, and then two shells of rockfill, inner and outer rockfill of different deformabilities. And this dam has been analyzed in several papers. There has been also attempts to make class A prediction for it. And here you have a number of marks for which we have data, and also for some extensometers. And you have here on the right the history of the water level in the reservoir. The reservoir was, well, there was an accidental partial filling in 86, and then the final filling in 87, 88. But you see also the record here of the rains, and you can see how those markers show settlements that can be quite, I think, quite nicely be correlated with the intensity of the rainfall. This is perhaps a more clear example. This is an embankment in the Madrid-Sevilla high-speed train. This is 40 meters high, schists and slates. Here you have the monthly rainfall record for a number of years after the construction of the embankment. Here you have the settlement rate, and you can see this strong correlation, very strong correlation between the intensity of the rain and the rate of settlement. Now, those trains run at more than 200 miles per hour. So I think that we have to be quite careful now in analyzing the settlements of these structures and how they are going to proceed and to develop in time. It is interesting to see here that this relatively small rain here induced also relatively small rate of settlement. You increase the rain, and there is an increased rate of settlement. You increase more the rain the following year, and well, it increases, not that much. This final rain here, plotted here, and no response. And the question is why? Now, what I would like to do is to show you that I think we are in a position to try to solve this problem and to predict the behavior of an embankment when you have this type of external actions, for instance, rain. I will make a very short review of the previous research. Perhaps Terzaghi is one of the first to address this problem, and he referred to breakage. So he related the collapse of rockfill with the breakage of particles. And then those are very interesting pieces of work performed here in the United States in the 60s, and they performed large diameter tests. They analyzed the scale effects. In 73, the very well-known work of Marsal in Mexico. Marsal was an Argentinian. He worked in Mexico, and he performed beautiful large-scale tests in a wide range of different rockfill materials. The well-known paper by Novary and Duncan in 72 about the collapse of rockfill, a very nice study in the laboratory. And also, this is, I think, an interesting work, the deformation, the time-dependent deformation of rock contacts, and in particular the effect of water in the rock contacts. I will simply show a couple of slides on relatively old work. This one, the odometer test on crushed rock, and you see what happened. You have an odometer, you load your sample, eventually it comes to a rest, to a relatively a small rate of deformation. If you wet your sample here, there is a sudden acceleration, and again it comes essentially to rest. Now this is for this material. You change the material, similar type of behavior. You see that if you compare the deformations after wetting with the sample that was initially wetted, you more or less get the same result here. And this has been checked again and again by different researchers. Now, if you compare the previous load settlement curves with the behavior of a single tip of rock, and this was actually the subject of the Clemens paper, you see how a single contact behaves essentially as the whole sample. So here comes the deformation, you wet it here, and then this acceleration, which indicates that probably the failure of those contacts and the failure of the particles had much to do with the overall behavior. Now, so if particle breakage is of fundamental importance here, what are the mechanisms of particle breakage? I will say, well, perhaps, and this is not explicitly said here, a major reason for the breakage is that the stress at the contact is high. But thinking in terms of, change of saturation or what is the effect of water, then there have been a number of explanations here. Loss of cohesion due to mineral superficial energy reduction, whatever that means, suction reduction, expansion of clay minerals. But I think that the theory that explains in a more convincing way, in my opinion, in a more consistent way, what happens is the idea of subcritical crack propagation, and here is an interesting reference. I will introduce some concepts, very simple concepts of fracture mechanics that probably most of you know. In fracture mechanics, we define a stress intensity factor which combines geometry, stress, and the length of the crack with this square root here. Now, the L here stands for different loading modes. The more common one is tensile, but you may have other shear modes here. And then the classical criteria is that if your stress intensity factor, which has all these parameters inside and effects inside, is equal to a property of the rock, which we call toughness, the crack propagates immediately. Now, subcritical crack propagation means that even if our stress intensity factor is lower than the toughness, cracks may also grow at some speed. Let's have a look at this crack growth. This has been analyzed by people working in material science, and what they tell us is that the strong bonds that are at the tip, they are highly stressed. They are affected by the presence of a molecule of water, so that a reaction takes place here, and these strong bonds become actually a weaker bond, and then this is not able to resist anymore the state of stress in this area here, and then that leads to cracking. Now, this reaction has been analyzed, and actually we have closed form equations that give us the velocity of crack propagation. And what it is interesting for us is that this velocity depends on the relative humidity of the atmosphere in which the crack is, and it also depends on stress. So this K here is the stress intensity factor in the crack. So this is a stress, this is geometry. So those are the two factors that actually can be handled by us, from an engineering point of view. And the rest are a number of constants that, in the theory can be explained, but I'm not going to enter into that. Another point that I would like to make is that relative humidity measures the potential of the water. There are alternative ways of measuring the potential of the water, for instance, in the atmosphere. One is the vapor pressure. Well, vapor pressure is relative humidity, essentially. But if you have relative humidity, you may also compute immediately, using this psychrometric equation, the total suction. This is well known for the people working, for instance, in unsaturated soil mechanics. The point is that relative humidity and total suction is essentially the same thing. Now, this theory has been checked. And on the left, you have results on glass. This is a brittle material, and there is a lot of results, and you have all those points which correspond to actual tests, and the continuous lines refer to the theoretical expression, so it matches quite well the actual the results from the lab. On the right, recent results showing you the velocity of crack propagation as a function of vapor pressure, and this is also consistent with the previous theory. Now, what you have here in the graph on the left is the crack propagation velocity as a function of a stress intensity factor in the horizontal scale here, and the different curves here refer to different relative humidities, from very dry atmospheres to saturation conditions. Now, if this is true, then we may perhaps immediately propose a conceptual model for a rockfill. In a rockfill, you have many contacts, and each one of those contacts, for each one of them, will apply this graph here. This is essentially the same graph that I was presenting. Here we have crack propagation velocity. Here we have the stress intensity factor, stress in our case, for a rockfill. And here you have the effect of relative humidity. Now, let's take one relative humidity, this particular curve here, for instance, in the middle, and it will divide, presumably, our horizontal axis into two regions. One on the left of this K0 this is a threshold value of the stress intensity factor. Towards the left, probably the velocity of crack propagation is very small, for instance, 0. In between K0, which is a threshold, this is a property, this threshold value and our toughness for this material, for this rock, we have a region in which any crack standing here will propagate at a certain velocity. And then, whenever a crack reaches this point here, it will propagate very fast, so this means failure, rupture. Now, we will have many cracks, and they will divide into those 3 regions indicated here, but whenever we change the stress, or we change the relative humidity, there will be a transfer of cracks from one region to another. There will be an acceleration of the formations. Some of them will immediately crack, and probably that will imply some rearrangement and some deformation. Now, the next logical step is to say, all right, let's then conduct tests in our lab using our Rockfill and then controlling not only the stress, but we know how to do that, but also the relative humidity. The theory provides us, I think, a good background to understand what may come out from this test, but strictly we don't need that theory anymore, I mean the subcritical crack propagation, to continue, but I think it's very useful to have that in mind. What we did a few years ago was to select a quarry. Actually, there is a dam that is being built with, out of this material. The work is now started. And so we crushed material, and we prepared a gravel, and we tested it under odometer conditions. The material is a quartzitic shale, and well, it's a relatively good material. This is the unconfined compression strength. It's like a relatively bad concrete, but it's not bad in general for a shale. And this is the cell that we built. This is the first cell. This is an odometer cell for samples up to 30 centimeters in diameter with relative humidity control. The most important feature of this cell is that we can circulate air with a given vapor pressure. And the vapor pressure is controlled here in a saline solution. So you circulate this air with a vapor pressure, and eventually, after some time, then some equilibration will be reached within the sample. The cell is prepared to measure horizontal stresses, also the friction, and of course the vertical stress, deformations, etc. And here is a picture of what we have in mind. The vapor will equilibrate in the big voids, but then we will have those cracks, and also it will control what is the energy of the water here, and therefore it will control the progression of the progress of the velocity of those cracks. You should measure the evolution of the grain size distributions just to know how the material breaks, and you can have a feeling of how this initial material, given by this green curve here, evolves, and you can also compute some measurements, some coefficients that tell you what is the intensity of breaking. But clearly, after this type of testing, you compact and then you break some of the grains. But then, once you have your sample, compression and flooding, etc., results in an increased proportion of smaller particles, etc., and you can analyze this type of results. Another interesting information concerning this material, and I will explain that now, is the retention curve of this type of materials, how they react against the water. Now, we have essentially 2 types of pores. The small pores inside the rock particles themselves, and look, this is the information for those for the rock particles themselves. The water content is very small here because we have a small porosity. But we were able actually to build this in the laboratory, this drying and wetting curve using different techniques. But however, if you consider the whole picture, I mean the aggregate, then of course the porosity is much bigger, and the actual full water retention curve for the whole material is something like that. If you impose a very, very small suction, you essentially drain all the water from the big pores, and only when you arrive at the water content of around, in this case, 4%, then you have this change in the shape of the curve, and certainly you have to reach very high suctions, 1,000 megapascals, in order to really dry this rock. And then I will discuss a little bit what are the results of some of the initial tests that we performed. Those are odometer tests in samples initially compacted to a normal Proctor energy. And I will present in a moment the type of stress paths. But some of those stress paths started in this way. You maintain a suction there, so a relatively dry material, and you load and unload, you load and unload them, simply because I was interested in knowing what is the yielding behavior of this material. And on the right you have the response of the sample, and you see that from the very beginning of the application of any confining load, if you remove the load, you get a substantial irreversible deformation. So immediately you have here a very clear picture of an elastoplastic type of behavior of this material. The actual stress paths that we use for all the tests are indicated here. I will describe them. In test number 1, we start in a dry position, a dry situation, low stress. We wet this material, and then we load it under saturated conditions. And on the right, you have the response in terms of void ratio or axial strains as a function of vertical stress. And then in test number 2 is more complicated. You load at a constant suction, so this is a dry material, you unload it, reload it, and here at this point, here an intermediate stress, you wet it, and then you load it again under saturated conditions. Tests 3 and 4 are essentially the same. We start again in a dry condition, we load it under dry conditions, and then we wet them at a confining stress. But there is an important difference between those two tests, which is not shown here actually. In test number 3, this transition from a dry to a wet state was made in just in one step. So we essentially saturated the sample. In the second one, I mean in test number 4, this transition was made in several steps of suction reduction until we got 100 relative humidity. However, at the end of this step, the sample was initially dry. So the pores had an atmosphere full of water in vapor phase. But I mean, looking at the specimen, it was essentially dry. And test number 5 actually is an intermediate stress path. And here you have some of the results. And you can see, well, some interesting features. You may see, for instance, that if you have a dry material, then for a given void ratio, for instance, or deformation, your apparent or current yield stress is much higher than the yield stress for the saturated one, which is this, the test number 1. You also see that the slope of the stiffness of the material is much bigger, and it's higher stiffness when it is dry than when it is saturated. You can also see that when you have a dry sample and you wet it, you end up in a situation which is close to saturated conditions. You may also see that the saturated compression line, those are, we may call them virgin lines, are more or less the same. Well, there are differences here, but remember, those tests are made on compacted samples, very difficult to ensure homogeneity. And also you can see that if you wet this test number 2 here, in this particular point, nothing happens here, but now the sample is saturated, and when you load it more and more, when you are already here, this material recalls that it has been saturated, and then it bends here, not here, and it follows the saturated line. So there are a number of features here that probably to some of you may look very similar to a regular unsaturated soil, but there are very important differences. Now those are test number 3 and 4. As I said, the major difference is that in test number 3, there was a big jump here. In test number 4, we proceeded in steps. The interesting thing, and when I saw this result for the first time, I said, wow, this is really very interesting, extremely interesting. You see how eventually we got the same final point here. So we got a step by step reducing the suction. Those are the actual steps in suction reduction. This is the black point corresponds to a sample with no liquid water in it. The green one corresponds to a sample with full of water. However, the final situation, the final collapse deformation is identical. Some conclusions of this initial set of tests. It seems that the unique normally consolidated line exists for a given suction. We have seen that they tend to reproduce to each other, different tests. If suction increases, the material stiffens. We have seen that. Yield stress decreases as the water content increases, or the other way around. We may define an elastic domain. The effect of wetting depends on the applied confining stress. It may either collapse or nothing happen when we are in the elastic region. And then collapsed states end in a saturated virgin line. And again, this may seem familiar to some of you. But let's look at some additional information. We may look at the time deformation curves. For instance, measuring in one of the tests. And you see we apply a load, and well, you have some instantaneous deformation, and then you deform it for a while, and this will continue. This is a logarithmic scale. Here you have some secondary behavior. And then we apply, so this will be the end. Then we apply a new load, and then here we have some instantaneous deformation, and then some delayed deformations. Now this is the effect of wetting. Wetting was completed here. What is the result of wetting? An acceleration of displacements, and then eventually we recover a new secondary behavior. But I mean, we have this type of information. We can actually have a look at the instantaneous deformations and the time delayed deformations, and we can try to understand how those two types of deformations behave. Now, from this perspective, the time, I call it the time perspective here. The instantaneous deformations, and I don't have here time to explain the details, but we realize that they increase linearly with applied stress. But what it is more important, perhaps, is that they are not affected by water content. And probably this is what you will expect, that if you rearrange some structure in a rock field, water content is not important at that time, because this is a purely kinematical type of problem there. However, the time-dependent strains, they also seem to increase, well, linearly or not. This is not fundamental with the applied stress, but what is fundamental is that it depends on the current water content. And also, we found that those time-dependent strains are very small if we have a very dry state, and they are also very small below a threshold confining stress. And probably that takes you back to the subcritical crack propagation theory. Remember that if we have a very dry state, the velocity of crack propagation is very small, or 0. And you remember this K0 value in that reference graph that I discussed before, that marked the beginning of crack propagation. And I said this is a threshold stress intensity factor. A threshold stress intensity factor translates here into a threshold confining stress. And we were able actually to find this confining stress, the threshold confining stress. Now, from the point of view of the mechanism then of deformation, we may perhaps synthesize a little bit those results. We have particle rearrangement. This tends to be instantaneous. And then we have cracking, failure of the cracks, of the particles. Whenever we have some particle crashing, then we are, from a conceptual model, in a region, the points, I mean the contact points, are in a region in which the stress intensity factor is higher than this threshold value. And again, here we may distinguish instantaneous. The instantaneous deformation will come if we reach the toughness, but most of the contacts will be under a time-dependent regime, and in our underlying conceptual model, we will have on each of those contacts a stress intensity factor which is in between the toughness and this threshold value. And then with this, we can move on a little bit and try to build an elastoplastic model for the deformation of a rock field. So we have this division here, instantaneous and time dependent. Okay, let's maintain that. Instantaneous, and we adopt this notation here, epsilon I, instantaneous deformations, and we have seen that those tend to be independent of wateration. They tend to be linearly related with applied stress. And then time dependent. The time dependent exists whenever our stress is larger than a threshold. This comes from the underlying theory. This comes also from the experiments. But we recognize that they depend on water action, so we should write them in this way. This should be a function of the prevailing suction, or relative humidity, or vapor pressure, any measure of the energy of the water. It has to be 0, or it should be 0, if our suction goes to a very high value, so we are in a very dry state, presumably in a very dry state, cracks don't propagate. And then it is relatively simple to build a model. I am going to build an elastoplastic model for one-dimensional conditions. For stresses smaller than this threshold value, let's simply relate the increments of stress in a linear way with the increments of stress. And when we have instantaneous and delayed deformations, then we have to add the two contributions, and we have to recognize that the delayed component depends on suction. And since both are related linearly to the stress, let's assume this very simple relationship here for the increments of deformation. The only thing we need now is to specify this equation here and to propose something for the elastic strains. And for the elastic strains, well, the simplest thing we can do perhaps is to say, well, stresses may induce elastic deformations. Let's assume this linear relationship here. Changes in water content may induce some deformations. Well, this is difficult perhaps to accept in a rock fill, unless the rock fill is made of shale, for instance. In a shale, this may happen. And then changes in suction or water content may lead to some swelling behavior or shrinkage behavior of your embankment. So let's complete the model with these water-induced elastic deformations, and we may use as a fundamental parameter the changes in the water content or suction or any other thing that measures the energy of the water. And the simplest thing is to say that the first is independent of water action, and the second is independent of stress level. Of course, we can remove some of these constraints and get more complicated models. Now, those assumptions are consistent with this type of theoretical behavior. Here you have theoretical behavior of a dry sample. You load it, at some particular point you wet it, and you have a collapse, and then you continue your loading under saturated conditions, you unload it, etc. And if you have a sample initially dry, and then you wet it initially, and then you get some expansion here, and then if you load it, this is essentially elastic because our stress is smaller than this threshold value, but here you begin to yield, and then here you have your normally consolidated line for saturated conditions. Now you can follow, this is an explanation of what you measure actually in the odometer. It is much more useful to consider that from the perspective of hardening plasticity, and on the left you have the stress plane. But I have plotted here not a stress axis, but a measure of the energy of the water. It can be water content, it can be suction here, but it has any implication of direct mechanical effect. However, if you start in a point such as this one, you load your sample, and what happens is that you drag your yield surface to a given point. And then, if at this given point you wet your sample, you drag again your yield surface to this second position here, etc. And then whenever you cross it, you drag your yield surface. What is the meaning of this yield surface? This yield surface is explaining us that the pre-consolidation stress, the yield stress, we'll call it the yield stress, increases when you increase your suction. And this was one of the results that I immediately told to you when I saw, when we were commenting the laboratory results. So simply this result, that suction contributes to increase the yield stress, is represented by this yield curve here. The wet path is indicated here. You start at a dry point, then you wet it, maybe some expansion, a small expansion here. This is given by our kappa W coefficient, and then you load it. You will drag your yield point. First, you have to go beyond this sigma y point. Nothing will happen before sigma y, but then as soon as you cross this sigma y, you will yield the soil, etc., and then you will be under saturated conditions. Now, the actual yield curves for the shale that we were testing look a little bit like that. The graph on the left refers to suction as a measure of the water energy. The graph on the right to water content. This is isotropic conditions, and here are a number of those yield curves, and you may see this shadow here, this gray shadow, and those indicate the places in which there is no any influence of water content. for two reasons, essentially. If the material is very dry, we shouldn't have any yield. If the stress applied is lower than the threshold stress, nothing should happen, no effect of water. So the effect of water is concentrated, or it can only be measured in the white area in both graphs. If you use water content, nothing will happen for water contents in excess of 3.5% for this particular rock, because beyond 3.2%, the material essentially, the relative humidity essentially is 100%. So it doesn't matter that you have 3 or 4 or 5 or 20% water content, nothing will happen. Now it's interesting to interpret these ideas now in a real problem. For instance, this is point B in the downstream shell of the dam. And what are the paths that nature actually is inducing in this point? You may have you build your dam, and then you are perhaps in a point such as this initial point here, and then some rain comes, and then it will induce some wetting at a constant stress, total stress. But then if you are in this point here, you will drag your yield curve towards this second point here, and then in doing so, you will move towards the right your yield curve. That implies irreversible deformation. This is a collapse. And then you may dry it because there is some evaporation here, and then you will follow this path number 2. And here, nothing will happen essentially. Maybe some shrinkage, but in a rock fill, you won't notice almost anything. But then you wet it again, this is a second rain, and it will take irreversibly to a third point here. Eventually, if you apply strong cycles of wetting, you may get to this saturated situation here. Your yield locus will move towards the right, and from that point on, nothing will happen essentially. And this is what actually has been measured in many rock fields, and I mentioned that to you before. Now, this is how the model fits one of the tests, test number 2. And then I think I will now summarize a few results comparing unsaturated soils with unsaturated rock fill. Collapse in a rock fill is associated with particle breakage and the subsequent rearrangement of a structure. In soils in general, we only recognize, in most of the cases, rearrangement of the structure, no particle breakage. Particle toughness is a fundamental property. Strength, in general, does not affect soil behavior. The effect of suction in the case of we have seen that, in the case of a rock fill, is to control particle breakage velocity. The effect of suction in a soil is to pre-stress soil structure. This is where unsaturated soil mechanics enters here. Now, in a rock fill, there exists a threshold toughness, and this comes from the underlying subcritical crack propagation theory. And we included that very simply through an stress parameter. We may do other things, but I think we should keep in mind that below some stress, nothing will happen. There is no such an equivalent concept in soils. Now, total suction controls water-induced effects. However, in soils, at least in well-behaved unsaturated soils, such as silt or low plasticity clays, in general, matrix suction controls water-induced effects. I always joke saying that, if you have an acid rain, it will induce a smaller collapse than a true, clean rain. Perhaps it's the only good effect of an acid rain. Now, delayed deformations and therefore collapse, because collapse is explained as an acceleration of deformations, is inhibited for very dry state. There is no such an equivalent concept in soils. And the final 2 comments here are perhaps of less importance. We found that the yield stress for the very dry state is a conveniently hardening parameter. In general, in unsaturated soil, the yield stress for the saturated soil is a good hardening parameter in terms of formulating the equations. And elastoplastic strains tend to be related linearly with stress in the case of rock, and they tend to be, as we know, linearly related with logarithm of stress in the case of soils. Now, the next logical step was to say, okay, let's then move into triaxial stress states. We have built this big cell, It has a number of features, measuring inside by a couple of procedures, the volumetric deformations. Everything is controlled inside. But the important feature is that we can circulate an airflow with a given relative humidity, which is controlled here. And we were able to, and we are actually now running a test in this cell, testing saturated specimen, testing specimens at a given relative humidity, constant 1. You have here with this, those scales are the same. You may notice how the relative humidity actually controls the behavior. It affects strength, it affects stiffness, it affects also very much dilation properties of the rock field. So with this cell, we can actually then play a little bit more, change relative humidities, and impose different stress paths. And some of the results for those are results of the simple triaxial test. But here are plotted the incremental plastic strains in an effort to understand what is the actual yield locus. And on the right, you have our best estimate at this time. These are very recent results of how a yield locus of a rock field looks in the QP plane. And by doing that, what we did was to load the sample to a particular confining stress and load it a little bit, load it, and load it a little bit. You reduce the confining stress, load it again under shear, etc. And we can collect all those yield points, and then finally, eventually, we may get this type of result. Notice that the stress parameters here are normalized, and this is why we have a lot of results here. And also, those vectors here indicate the direction of plastic strain, and this is useful to develop elastoplastic models. You may also look at the difference between the strain, the grain size distribution curves for saturated specimens and for dry specimens, and certainly there is an important difference, and you can quantify that, etc. At the end, we have proposed a constitutive model for a rock field that takes into account the effect of relative humidity. Those are the features of the model. One interesting feature, and the only one I'm going to mention here, is that we made the degradation of the rock field dependent of the effective plastic work. And the effective plastic work was defined as the difference between the total plastic work and the plastic work necessary for rearrangement. The difference probably is associated with particle breakage. And in a PQS plane, perhaps one of the simplest way to formulate a model is to select a cap, which is simply this line here, and then the effect of shearing is taken into account by this eta q over p equal constant line, and then this is extended into the suction regime. But this is not that far from this yield curve that we have seen before, coming from actually directly from the experiments. There is a paper presented recently at the published in the Soils and Foundations. You may have more details. And here simply some comparisons of this model predictions with actual result, which is not bad. Some things had to be improved, some of the stiffness, for instance, at the small deformations, but overall, for a given set of constant, is not bad. But we have to do something else if we want to analyze a large structure such as a dam. We have to be able to predict or to compute water transfer, the flow of water. But this is a very complicated material. So you have, as I said before, a porosity, a small porosity in the rock, small pores, and then we have the big voids in the rock field. In a state of lack of equilibrium, probably, we may define two energies of the water, or two suctions, if you like. One prevailing at the big pores, and the other one at the small pores. So those entities are, I mean, the porosity is so different that probably the material can sustain those different suctions for a while. Of course, it can equilibrate. So this is, in a phase diagram, very simply, what I mean. We have the macro voids and the micro voids. The micro voids corresponds to the actual rock particles. And the micro voids can actually be unsaturated, we have seen the water retention curve for the microvoids, and then we may define even a porosity, certainly for the microvoids, and also a degree of saturation for the microvoids. And then we may speculate a little bit what are the flow processes. We may have free water flow going around the big particles, the macro. Probably capillary phenomena has something to say here, superficial flow. Well, we may try to generalize Darcy flow by simply specifying that the permeability is a function of the degree of saturation, as we do in unsaturated soils. But here we have this potential, total potential, controlling macro potential, controlling the flow of water. We have also flow in vapor phase, which maybe is very important and more relevant in many cases. We have to include that. And then we move into the particles, the micro, and then we define here a different potential. And the point now is that there will be a transfer between the two. This transfer is important because it will wet or dry the particles themselves. Now, the hypothesis here is that this local flow, which changes the local water mass in the rock, is proportional to the difference between these two potentials. So this is a linear type of approach, very simple way. And we can actually now try to compute the local water content. Since we have information, we can actually write those equations. The pore volume for the micro is simply expressed as this. This is the porosity for the micro part, and this is the porosity for the macro one. And we multiply this pore volume by the density of the water and the degree of saturation, and then we have the total mass. And then any change of this mass as a function of time, and actually we can make a derivation here, will be matched by a change in local degree of saturation within the rock particles, and the hypothesis is that this is proportional to the difference of the two energies of the water. Notice that if we introduce here some water retention curve, and I have shown you one at the beginning, certainly you have here a differential equation. It may be nonlinear, more or less complicated, but you can solve it at a local level very simply. And then let's have a look at the global picture. We may then formulate the water mass balance at in the whole rockfill. This is liquid water, this is vapor. Those are the flows of liquid water, the flow of vapor. And this is the transfer between the macro voids and the particles. And this transfer term, we have now how to compute it. We add stress equilibrium, we add stress-strain law, and then we have a working procedure to solve this type of problems in rockfill. And we did that. We put everything in finite elements. Over the years, we have developed a computer program to solve this type of problems, and we simply keep changing constitutive equations, and then in this case, we added a few other things. And then we could try to solve this problem. This is the rainfall record for this Madrid-Sevilla, you remember, a 40 meters high embankment. And then, well, of course, I didn't have any information of that rockfill, but it was a schist, a slate, and I had information of the slate, the shell that I've been testing in the laboratory. So I said, okay, why not simply take my properties from the lab, and then I will run this boundary value problem applying this rainfall record. And this is what happened, and this is quite surprising. So this was simply a column 40 meters high, and in red you have our results from Code Bright. This is the finite element program, and in black the actual results. And you see, the interesting part is that this is the first rain, this is the second rain, you have an increase in velocity. The third rain, it was much higher, it doesn't increase too much. The fourth rain, nothing happens. The points have already yielded, they are already wet, and then nothing will happen beyond this point. And then Beliche Dam. And this is my final example. Beliche is known because this is a French, I said it's a Portuguese dam, and it was studied in the National Portuguese Laboratory for Civil Engineering, and for many years they performed many interesting tests, large-scale tests. The dam was heavily instrumented, so we have very nice data for this dam. For this case, we need an extended model. Instead of using the more complicated model, we simply extended the concept that I've mentioned for the isotropic or one-dimensional case into the three-dimensional case, the triaxial case, by simply specifying an elliptic yield condition that may, well, of course, I mean, this has to do with camp clay, but even if this is a rock fill, I think it works in a reasonable way. And for you to have an idea of how, I mean, what parameters we need, those are the parameters, but those parameters have a physical sense and they can actually be derived from actual tests. So you can follow them. Those are compressibility for dry, saturated states, elastic compressibility, the solid shrinkage coefficient. This simply gives you how the stiffness changes with water content. You only need a couple of tests to, let's say, dry and saturated to establish that. Poisson ratio, friction angle, and then this isotropic threshold yield, which is always there, the parameter. And as I was mentioning, there were a number of very interesting test results with large diameter cells. This is a real effort that was made in the Portuguese National Laboratory. There are very interesting publications by Veiga Pinton in this period. And then we simulated those tests, the triaxial and the odometer test, and we back calculated the properties of this material by simply trying to simulate the test results. And I'm going to present you as a comparison what we did to derive model parameters. On the left, odometer test, large scale odometer test. On the right, triaxial test. The red curves indicate the model, the black ones, the actual test results. And of course, you may see some differences, but if you go along, this is the inner shell, this is the outer gray vaca shell. Always some difficulties to capture the latency. You have to improve the model to capture better the latency, but this overall is not bad. And then for the clay, we use a simple model for unsaturated soils. It's an elastoplastic model. We call it BBM. It was published in 1990. BBM stands for Barcelona Basic Model. And you see how it reproduces the behavior of the inner core. And also we had some foundation soils. And well, I say here BBM, but this is typically a camp clay type of model. Again, camp clay, some difficulties to model some of the volumetric change induced by shearing, but not bad overall. And with that, we produce this discretization of the dam, and we try to follow the actual construction. Construction started in 82. There was some heavy rain, intermediate heavy rain, with some unexpected filling of the reservoir in 85, and then the dam was completed, and the reservoir was essentially filled in 88. And those are the stages. Those are the stages in construction. Actually, those layers were applied layer by layer. We continue with that. This is the unexpected water filling on the upstream, and this is the construction, final construction, and this is the final filling of the reservoir. Those are the boundary conditions, standard boundary conditions, except that we follow the application of rain. So all those blue dots here indicate rain. So during construction, we were following also the application of the rain. And of course, the reservoir action was applied in the upstream shell. And here are some results. It's always nice to put some colors. These are the stress distributions. You may have a feeling for some arching effects at some particular time between the central clay core and the rock fields, and that changes in time. Those are the stress distributions. Those are the water pressures. You may identify, notice that the scales are not the same. You may identify the actual water saturation curve. We don't need to compute any water saturation. This is a fully integrated analysis. So you simply look at what is the contour for zero pressure, and here is the contour line for the saturation line. And of course, this is unsaturated, etc. Those are the settlements. You see how this inner shell, which was more deformable, behaves, and later you have more deformation also of the core, and how when you wet this part, this unexpected wetting, you get some collapse of those shells here, so the deformations move toward the right, towards the left, and then as we completed the dam and we raise the level, there is a more symmetrical behavior now. And here is a comparison of the actual settlements as measured in some extensometers. Those are the extensometers, I1, I3, and I6, with our calculations. Of course, those are calculations much after they were measured. Well, they are quite good, especially for the the upstream and the central one. More difficulties in the lower, in the downstream shell. Probably the laboratory didn't represent well the actual deformation in situ. But overall, the behavior, I think, is quite good. And also, we were able to compute the deformations along time. Those are the red lines. Again, this is the model. This is an indication of how, in a particular node, the water pressure changed, just to indicate where the heavy rain is. And you see how, and this is very interesting, how the model predicts the acceleration of displacements. This is matched by, in some cases, not always, with the actual measurement records. This is for J54. This is for J40. Again, we were able to follow up, more or less what are really happening. We need to introduce probably some creep here. This is not included yet into the model. Now, I am arriving to the conclusions now. From a general point of view, what I think is that rockfill deformations are a combination of particle rearrangement and particle breakage. And then particle breakage, which is a fundamental ingredient here, is controlled by stress and relative humidity. And the underlying fracture mechanism is described here. The relative humidity in the open rockfill pores and the stress intensity control essentially the rate of deformations, in the sense that when you increase relative humidity, the rate of deformations increase. When you increase, of course, stress, the rate of deformations also increase. Collapse is explained as an acceleration of fracture propagation velocity of cracks in the rock. No mechanical effect direct of the water. From a constitutive model point of view, I've shown you some ideas to develop an elastoplastic compression model for the rockfill. The model, I think, is very simple, but however, I think it captures quite well the experimental behavior of rockfill. This isotropic or compression model essentially describes what is also called as cap behavior. If we move into more general yielding, I have described very briefly, because certainly I don't have time here to go into details, but those two yield surfaces are able to describe in a general way the behavior of a rockfill. And I simply mention here that rockfill degradation was made dependent of effective plastic work. So this is not a strain hardening type of model, but a work hardening type of model. But I think that the ideas of work hardening as an alternative to a strain hardening are very appropriate for a rockfill, because work is what actually breaks the particles. And the applications, I've shown a few applications on dam and embankment behavior. I think collapse phenomena is always the determinant aspect in dam and embankment behavior. I've mentioned that some of the embankments that we are recently building belong to those high-speed train lines, and we have to be careful and to be very precise on the estimation of those deformations. It is very interesting to see, I mean, going through the literature and the direct experience that we have, is that the rainfall-induced collapse may be as significant as the reservoir-induced one. So it's not a question of saturating the rockfill at all. It's a question of changing the relative humidity, and the rain can be as effective as the water, the liquid water, to change relative humidity. This is why, I mean, those numerical methodologies, ad hoc approaches, I don't think they should be used. They skip some very important effects, and some important features, for instance, how to extend this analysis into the time, cannot be actually realized by using those simplified approaches. I have shown how to build or to reproduce the behavior of Beliche Dam. I think the field behavior is quite well explained, and we will publish this analysis of Beliche Dam, I think, in the near future. However, there are a number of limitations, and I will say additional work is required that I have not mentioned. Scale effects This is a very important problem, how to relate those big sizes to our laboratory scale, no matter what you use in the lab. I mean, you cannot actually match the actual conditions. We should improve the validation against more field measurements. Time effects have not directly included. One thing that is important maybe is the degradation of the rock field against cycles. This can be analyzed in the laboratory, but certainly this work has to be done. And perhaps from a fundamental point of view, the most challenging problem ahead is how to relate the macroscopic behavior as we observe in large-scale tests or in the field with some fundamental rock properties, for instance, such as toughness or the velocity of crack propagations, so that we can build models in a better way for the future. I would like to acknowledge some of all of them have been doctorate students in our group. Luciano Oldekop is now professor at the University of San Juan, Universidad de San Juan in Argentina. Carlos Chavez, he came as a professor, he was already a professor in la Universidad de San Luis Hidalgo in Mexico. He's about to finish his doctorate. Enrique Romero, he did a very good job a few years ago, a beautiful thesis on expansive soils, compacted soils. He is now the director of our soil mechanics research lab, and to our particular National Science Foundation because of the support that we have received from them over the past 10 years. Thank you very much for your attention.
Time for some discussion of the paper. Who wants to be first? I was holding you for last. Okay. We'll leave you for first. Start it off.
Oh, okay. Yeah, if you had to give us a classification of Rockfill, like good Rockfill and bad Rockfill. If I wanted some Rockfill grains that did not collapse, and all the way to the other end where the Rockfill grains would really collapse, could you give us some types of Rockfill to stay away from and some that are good and so on?
Well, I mean, a good rockfill will be a quartzitic type of rockfill. There you can expect, of course, some crack propagation, etc. Still, always some collapse, always, and some delayed deformations, but certainly the toughness of this material is quite high. Very good and indurated carbonate rocks also, I think, are good. Whenever you include some clay, for instance, in marls, even high-quality marls, then the quality decreases. Shales, of course, are the worst. We have been testing a quartzitic shale. This is about the best shale. This shale was of a Cambrian origin, so it was really indurated with siliceous cement, however, highly fractured, so it was prone to, as I have seen, to collapse. This is an intermediate material. You have real shale, then it evolves towards soil, essentially, over the time. So, well, and then basaltic rocks tend to be good also. Yeah.
Yes.
Dr. Alonso, are you recommending to add water to the rockfill during placement to avoid the sudden collapse characteristics where you can have more controlled settlement?
Exactly, absolutely. And this wetting should be, and now the point that actually comes out from this work is that what you should ensure is that the wetting actually saturates the rock particles. So I think that the control in the field should be to actually look at the saturation of the particles, boulders. If they are saturated, then the behavior will be much better, of course. So that should be done, but not simply, I mean, wetting it. The control should be at the particle level. So from time to time, a sample of the rock itself, and let's see if it is saturated.
In earth drill dam construction, compacting on the dry side of optimum is desirable to avoid a lot of stress associated where the earth embankment comes in contact with the rock in the valley.
You mean to maintain a high stiffness?
Yes, to avoid tearing and shearing as you increase the amount of settlement. Is that, macro effect also
well, if you move into, well, you know there are two schools of thought typically associated with compaction. I certainly belong to one of them, is to add, to compact at the optimum, or if you can, at weight of optimum. Because my experience with fields compacted dry of optimum, even if you apply energies of the Proctor energy, normal Proctor, or even a little bit higher, is a bad experience. I mean, you get collapse deformations, you get cracking, so it's better to live, during construction operations with a relatively, not a good situation because you have relatively high water content, but try to compact at the optimum or at weight of optimum, and then you will avoid those complicated problems later. Crackings, sudden deformation because of rain or water impoundment. Certainly, this is my feeling.
Okay, back here on the side.
What about the sigma 1? Is it a material property? And what's the influence of compaction energy on sigma 1?
All right, I don't have that information. It is a material property, but I can show you. Can I go? Oops. One interesting result that I skipped. And actually, I cannot answer you exactly because we don't have enough information, laboratory information, to tell what is the effect of compaction energy on sigma y. But sigma y, I don't think is very much related to compaction energy. It is a fundamental, probably, I don't know, fundamental property of the rock material itself. So it shouldn't be affected too much by compaction energy. However, compaction energy produces a different distribution of particles in the rockfill, and then this may imply something. This is the computed settlement for this embankment of the Sevilla-Madrid line. Of course, they didn't measure anything. So I wish they had installed continuous extensometers along the embankment, but they didn't do it. But what we calculate is that in the upper part of the embankment, nothing happens, and then all the deformation is explained in the lower part of the embankment. And well, this is a different curve for different times. But this is what should be if there is a threshold sigma y value. So we couldn't compare this with anything. But in this dam, in El Infiernillo Dam in Mexico, Marsal in '76 in this beautiful Casagrande volume, it was a red book many years ago, he published the results of the instrumentation of the El Infiernillo Dam, and he published these results. Those are extensometers results. You see those are profiles of settlement for different times, and you see that the upper part, the upper 50 meters or so, or no, not so much, 40, 35 meters of El Infiernillo Dam, and at this particular location here, D2, this is close to the crest of the dam, didn't settle. The settlement comes from the lower part. My explanation now, these things have to be perhaps verified more, but my explanation is that the sigma y value for this rock in El Infiernillo was high enough, but it's very simple to compute how much it is in an approximate way, so that stresses in this range of stress, below 35 meters of rock, which is you multiply 35 meters by 1.8 tons per cubic meter, and this gives you a stress. This is probably the threshold stress for the material of El Infiernillo Dam on the basis of this result. Okay?
So does that mean 35 meters So it's close to the sigma 1 over the unit weight of the rock.
Exactly, yeah, for one-dimensional conditions. I mean, for one-dimensional conditions, you see that nothing happens up to here, down to here. So for stresses below those 35 meters, you don't have any effect of water action, no deformation.
That means for a good embankment, the larger the sigma y over the unit weight is
yes, which means that if your material, I mean, if your material is strong, I mean, in the sense that your K0 value, this threshold value is high, this is probably the case in a quartzite or in a basalt, then it won't deform too much. This is what it's saying. Right.
Just 10 questions, please.
How is the issue of, say, regular drying? You listed cycles of the cycles of relative yes. to be investigated. Yes. What is your opinion on that?
Well, I will tell you in a year from now, probably. But my feeling is that, as in any other material, well, no, not as in any other material. If you apply cycles of wetting and drying to a rock, especially if the rock has some clay, you induce damage in the rock. The reason is that if it has clay, this drying and wetting acts as it controls the deformation of those stacks of clay particles, and then they act as internal jacks, and then you eventually break the rock. So if this is the case in a rock, it will be the case in a particle of rock, and then within the rock field. So I expect that if you have a clay rock or a shale, or probably not in other type of rocks, yeah. This thing, I mean, this application of cycles will eventually induce some degradation of the rock. So this will lead to a degradation of the rock. This is an easy experimental research. You can do it and quantify that, and so it is relatively easy to do.
Yes, one more.
You said you use 2D low-key. Do you consider the low blast curve as your surface or your low?
I don't understand. Do you consider what?
You said you use 2D low-key in your model.
Oh, yeah.
Do you consider the low blast curve as your low curve?
I don't know if I understand. If I consider, you refer to the two yield curves, those are straight lines, considered for the generalized model, right? And then?
So what's the other yield surface?
What?
What's the other yield surface? The loading class.
Oh, the other one? Okay, sorry, yeah. You simply extend this. Okay, I'm going to show you. Okay, this is for the saturated plane. So this is for saturated conditions. So this is this simple cap here, and this is the shear yielding, okay? And then this is extended into regions in which you have an increased suction by simply saying that this cap here moves, and you may recognize here this yield curve here, which is the one that I derived for the one-dimensional analysis. So for the odometer test, you remember, eventually for isotropic conditions, you had an influence of the degree of saturation or the suction. Okay, so one very simple procedure to generalize and to obtain a fully three-dimensional yield curve here is to take those two straight lines and then to extend those following this yield curve under isotropic conditions into suction. Okay? That's it.
Jean-Louis has very graciously asked me to present you this plaque, which recognizes your participation in the conference as the 11th Buchanan lecturer.
Thank you very much.